Hi, class. I've put together another example for us where in this case, we're going to look at a one sample, a test on a mean, but in this situation, we do not know what the population standard deviation is. So let's go ahead and get started. Let me see if I can make our screen show a little better. All right. So this material comes out of section 9.3. And again, the important part to this is that the variance is unknown. So how will we how does that change from the previous examples we've been working where the variance is known? Let's read our example. An important quality characteristic of water is the concentration of suspended solid material. A sample of 60 specimens from a certain lake revealed a mean of 59.87 parts per million and a sample standard deviation of 12.5 parts per million. Test the claim that the population mean, mu, is equal to 55. And we are to use an alpha significance level of 0.05. All right, we're going to go through all 9 steps as before. So we're going to be utilizing the 3 different methods where we can assess that claim. But to start off, let's talk about our parameter of interest. So the parameter of interest in this case is concentration of solid material. And the units are parts per million. All right, so next we have our hypothesis statements. So the null, the statement of status quo, or the currently believed or claimed values, and then the alternate. So in this case, we're saying that the mean is equal to 55 parts per million. All right, so for some reason we want to validate the claim, we're suspicious it's something different, and that's the reason for conducting the test. Now, our problem statement didn't make any kind of a claim, well, we think it's actually larger than 55, we think it's less than 55. Nothing was made other than, can test the claim. So that means we're going to look at not equal 55 parts per million. Not equal to that. So our significance level was given to us 0.05, which is a very common one and one that you will likely be using in the industry. All right, well, we're set up, ready to go. So now we need the appropriate formula for analyzing the evidence. So let's take a look at the flow charts. So please reference your flow chart for the hypothesis tests. One sample hypothesis tests. I've got a few things on my screen that are in the way. Let me get those out of the way for us. Okay, so here we are. One flow chart, one sample, that's confidence intervals. Let's go there. And one sample hypothesis tests. So as always, begin in the upper left-hand corner where it says target parameter. The first thing we need to decide is, are we dealing with proportions or are we dealing with a mean? And in this case, we're dealing with a mean. So we'll move our way down. Is sigma known? In this case, no, it is not known. We had a standard deviation, but that came from the sample of 60 specimens. So in this case, no, it is not known. So we're going to have to work our way down. The next question is the population normally distributed? So as I mentioned before, we have various tests that we can actually assess whether the population is normally distributed. So in this case, for right now, we're going to assume yes, and I will be talking about the ways that we can make that assessment in further lectures. If in fact, for some reason, it is not normally distributed, then we're going to use non-parametrics, but that will be outside of what we cover in EGR 280. So that leaves us with, this is the formula that we're going to be using. So you notice we're no longer calculating a z. We're now calculating a t. And you may recall that I've said that the t is like a conservative z. And the reason is since we do not know the population standard deviation, we don't know exactly what that distribution looks like. So the shape of t changes as we gain more information. As n gets larger, the t changes shape, and eventually as n gets large enough, will start to look like the z. But for right now, we're at the t. So there's our formula. So oops, there we go. So t is equal to our sample mean minus the population mean, that is the assumed value in our null. And then we only have a sample standard deviation, and then divided by our sample size. So let's put in what we know. So the sample mean out of the 60 samples was 59.87 minus the assumed mean, or what is believed to be the mean, divided by sample standard deviation and divided by the sample size, which was 60. So once I compute that, that is equal to 3.018. Okay, just like we've been doing so far, now this is our evidence, and we have to compare that evidence to what we have decided would be considered beyond a reasonable doubt. So we're going to draw a picture of our null hypothesis and then identify beyond a reasonable doubt. So these are our x values, and now instead of now instead of z, we have t. So our mean, our accepted mean, was mu equals 55, and that corresponds to a t-value of 0. So in order to now identify the regions, the rejection regions, or the regions corresponding to beyond a reasonable doubt, we go back to that alternate hypothesis. The alternate hypothesis, and that was not equal. So the important piece here, what we're looking at here, is that not equal. That means that we have two rejection regions, one at the lower tail, one at the upper tail. So now I need to know, well, we had alpha equals 2.05. So I need to put half of that here, so 0.025 there, and half of it here, 0.05 divided by 2, which is equal to 0.025. So half in the upper tail, half in the lower tail. So what I need to know then is what t corresponds to this upper tail of 0.025 and what t-value corresponds to the lower tail of 0.025. So I'm looking for a t of 0.025, but there's another piece that we need, and that piece is actually going to be the degrees of freedom. Again, the shape of the t distribution changes with n, the number of samples. The degrees of freedom is n minus 1, n minus 1. So I pulled up our lecture slides where we talked about the difference between reading the z-table and the t-table. So let me share that screen with you. Okay, so there is our z-table. There's the z's. And remember, the z values go along the, are along the left-hand column, and then the hundredths digits across the to identify which column to look into. And then the area under the curve is what's in the body of the table. You may recall that I said the t is constructed, almost inversely of that. So let's take a look at our t. So the t distribution then, we have the t values now are in the body of the table, and the area, the percentages then, are given up as the headers of the columns. So the left-hand side, that's the sample size, or what we're going to call degrees of freedom, which corresponds, a degree of freedom is equal to n minus 1. Degrees of freedom equal n minus 1. So that's a reminder of how we read the t-table. So for our problem, let me go back to it so you can recall. For our problem, we needed to find a t-value of 0.025, and degrees of freedom will be 0.025 n minus 1. So that's 0.025. And remember, we had 60 samples, so 59. So let's look back at the t-table and see if we can't find the right value. Excuse me, I'm going into I've got to go back to a different screen than I was headed at. I need to go. Okay, t-table. There we go. It's not showing up. I'm sorry. Thank you for your patience with me. There we go. All right. So 0.025. So we're going to go along where the area is up at the top and find 0.025. Find 0.025. And then you have to scroll down that column until you get to 59 degrees of freedom. 59 degrees of freedom. So what you see is we go from 50 to 60. There is no 59. So in this case, let's just go to the closest one, which would be 60. So I've got to go back to 0.025, get my column right again. And so that corresponds to a t-value of 2.0. 2.0. So that's the value that we need. So that's equal to 2.0. One thing that you noticed is there are no negative numbers on the t distribution. So what we do is we just make it. We just are going to add a negative number. So 2.0 for there, the area above our value. So the area above a t value of 2.0 is 0.025. There are no negative values, so I just make this a t-value of minus 2.0. All right, so this now identifies the areas that, this is our region where we expect our evidence to be if the null is true, and then the area beyond a reasonable doubt is in here and over here. And over there. So the next step then is to take our evidence and put it on our graphic of the null hypothesis with the critical regions identified. Our evidence is 3.01. So there's t of 2.0, so 3.01 is going to be somewhere over here. There's our evidence. Oops. Evidence. Okay, so there's the evidence right there, sitting right here at a t-value of 3.018. So let's interpret that. Remember, everything is based on given the null is true. So if our null hypothesis is true, we expect our evidence to basically be in that shaded yellow region. Anything that's in the red was beyond our reasonable doubt. It was unusual. It was surprising. If the null is true, it's surprising to have values out there. So let's write this down. G and T, the evidence is surprising. You didn't expect it to be there if the null is true. So since it is surprising, we reject our null. We reject the null hypothesis. Reject the null. All right, that's the classical hypothesis test. But again, did I almost reject it? Was I, really close, far away from rejecting? So we're going to calculate the p-value. Now the p-value, I'd like to, I'm going to go over here just to get a little bit of some clean screen so we can look at it a little more carefully. So here was our rejection region at t equals 2. And our evidence is sitting over here. There's the evidence at a t equal 3.018. So how close were we to rejecting? How close were we to not rejecting? That's what p-value tells us. So I want to know, all right, this is what we got. And remember, this goes all the way out to positive infinity. So what I want to know is I want to know the area, the probability of getting what we got or more extreme. Again, p-value, the probability of getting what we got or more extreme. So I want to know this area, what we got or more extreme. As a reminder, the more extreme is defined by our alternate hypothesis. And we had a mu not equal to. So that not equal to tells us that we have two directions of more extreme. So there's where our actual value was. But we're also going to put a little bit of a dotted line one over here at a t is equal to negative 3.018. And I'm going to put a little what we got or more extreme. And that's kind of a dotted one too, right? Because our data was a positive one. But since our alternate is two-sided, we actually have two areas due to the symmetry of the t distribution. And that our alternate was two-sided, we have two areas of getting what we got or more extreme. So how are we going to calculate that value then? So let's go down and look at our p-value. So we want to calculate the p-value then. We say the probability of t greater than 3.018. Greater than 3.018. Since the alternate is a two-sided, we're going to multiply that by 2. Multiply by 2. All right, but let's just concentrate on getting this piece right now. So let's look at we need to look back at the t-table. So here's our t-table. And how we find the area greater than t equals 3.018 is you go down to your degrees of freedom. Go down to the degrees of freedom. And remember, ours was 59. Our table doesn't have a 59. So we're just going to go to 60. That's the closest one we have. Now, software would tell us exactly. Your calculator will tell you exactly. But we're using the t-table, so this is the best that we can do. So I'm going to just choose 60, as being closest to 59. So lock yourself into 60. And what I mean by lock yourself into is you have to stay in the row corresponding to degrees of freedom of 60. And then move from left to right until you find 3.018. And you can see that 3.018 falls between the values of 2.66 and 3.232. So our evidence, 3.018, falls between the values of 2.66 and 3.232. And again, that's in row 60, the degrees of freedom of 60. So follow those two values, the 2.660 and the 3.232, follow them up to the area, And so that's between an area of 0.001 and 0.005. 0.001 and 0.005. So okay, so it was between 0.001 and 0.005. That's where our evidence fell. So without software, without your calculator, using a t-table, we're going to end up with a range for our p-value. Now, let's not forget this step though. Since our alternate was a not equal to, we need to multiply those by 2. So now I'm at a 0.002 and 0.010. 0.002 and 0.002. So we've multiplied by 2 then, so let's put that in terms of our interpretation. So given the null is true, there is, and all we can say is the interval, so between, there is between a point, let's see, 0.2, a 0.2% and 1% chance we would get what we got. So remember, p-value is support for the null. A 0.2 and 1% chance that we would get what we got if the null is true. So that offers very little support for the null. So reject the null, reject the null, reject the null. If the p is high, the null will fly. If the p is low, the null must go. So that is not a lot of support for the null, so let's reject it. And then we're going to do the confidence interval. Let's look back at our screen for where I want you to look is your flow chart for the confidence intervals. So here's our flow chart for confidence intervals. One sample. Target parameter is a mean. Is sigma known? No. Is the population normally distributed? We've discussed that. We're making the assumption yes. So that leaves us with this formula for use the t-distribution, this formula then for our confidence interval. And you did that in some of your homework, but here's going to be some more practice for us. Okay, so let's write out that formula. X bar plus and minus t alpha over 2 s divided by square root of n. Let's plug in what we know. So the sample mean was 59.87 plus and minus. Let's leave that one blank and get back to it. The sample standard deviation was 12.5 and we had 60 points. Do note that we're using n equals 60. The only time that we take n minus 1 is when it actually says degrees of freedom, when we're looking in our t-table. But when we see n, it means n, so n equals 60. So now we're back to t alpha over 2. Just like we did before, that's 0.05 divided by 2, so we need a t of 0.025. But in order to look up a t-value, we need the degrees of freedom. So degrees of freedom, and that is equal to n minus 1. So I need a T at 0.025 and 59. And we used that up here as our, we found that up there when we were looking for our critical region, our critical values. So that's 2.0. So I'm going to plug 2.0 in there. And when I work that out, I get 56.64 less than or equal to the mean. Remember, only population symbols in a confidence interval. And then 63.10. So there's my 95% confidence interval. Quick reminder, the interpretation, we are 95% confidence that the true mean falls within that interval. So how do we use this now to assess our research question? Well, we go back and we find the parameter, the value that's given in our null hypothesis, the believed value. So that's 55. So will 55 fit into our interval? So 56.64 less than or equal to 55, less than or equal to 63.10. So that is not true. So not a true statement. Reject the null. 55 does not fall in that interval, so reject the null. So just a quick summary. We used classical hypothesis testing, and our evidence was in the rejection region, so reject the null. We looked at p-value, the probability of getting what we got if the null is true was a very small chance. So we're going to say reject the null there, and then we built the confidence interval. It didn't contain our population, our believed population value, so once again, reject the null. So how would we put that? We'll say the evidence supports rejecting the null, in favor of the alternate, in favor of the alternate hypothesis. All right, so that manufacturer, or this claim that the population mean is 55 is rejected. The concentration of solid material is something different. The mean is something different than 55. I hope that helped. Thank you very much.